58 years, 2 months and 14 days. That's how long Mount Semeru has been erupting without stopping. Until today. At precisely 2:47 p.m. local time, the volcanic countdown that began in 1967 suddenly froze. The ash plumes that have painted Java's skies grey for nearly 6 decades vanished. The seismic tremors that local residents use as a geological heartbeat fell silent. The volcano that never sleeps just closed its eyes. Emergency monitoring stations across eastern Java are detecting something unprecedented. Pressure build-up 400% higher than Semeru's normal eruption cycles. The mountain that has been safely venting volcanic force for 58 years is now trapping it all beneath a crystallized dome. Volcanic mathematicians describe what's happening in terrifying terms. Semeru's continuous eruption has been Earth's pressure release valve for Java's entire volcanic system. Now that valve has sealed shut, and 58 years of accumulated magma energy has nowhere to go except up. Historical analysis reveals only one comparison. Mount Tambora's explosion in 1815, after a period of unusual quiet. That eruption ejected 38 cubic kilometers of material into the atmosphere, triggering global climate collapse. Summer never came in 1816. Harvests failed across Europe, Asia, and North America. Millions faced starvation as volcanic ash blocked sunlight for months. But Tambora's explosion released pressure that had built up over centuries. Semeru contains 58 years of continuous volcanic activity compressed into a single explosive potential. The mathematics are simple and horrifying. If Semeru's trapped pressure releases all at once, it could inject enough material into the atmosphere to trigger the first man-made ice age in human history. So when Mount Semeru's 58-year eruption finally reaches its explosive conclusion, will the volcanic winter that follows affect just Indonesia? Or are we counting down to the climate catastrophe that starves billions and reshapes civilization as we know it? The last time a volcanic eruption changed the course of human history, it began with silence. April 5th, 1815. Mount Tambora in Indonesia exhibited unusual quiet after months of rumbling. Local residents thought the danger had passed. Then on April 10th, 1815, Tambora exploded with the force of 800 megatons, the most powerful volcanic eruption in recorded history. The explosion was heard 2,000 kilometers away. Ash clouds circled the globe for months, but the eruption itself was just the beginning. As volcanic debris blocked sunlight across the northern hemisphere, global temperatures plummeted by nearly 1 degree Celsius. 1816 became the year without a summer. Crops failed from Europe to North America. Famine spread across continents. An estimated 71,000 people died from starvation and disease triggered by Tambora's climate disruption. That catastrophic precedent now haunts scientists monitoring Mount Semeru, the volcano that's been erupting continuously since 1967, longer than any other active volcano on Earth. Semeru sits on Java's eastern spine, part of the same volcanic arc that produced Tambora. This 3,676-meter giant has defined normal volcanic activity for generations of Indonesians. Its near-constant strombolian activity, characterized by small explosive eruptions occurring at intervals of 10 to 30 minutes, have been a geological constant. Regular ash emissions reach from 400 to 900 meters above the summit. Predictable pyroclastic flows run down its southeastern slopes, a rhythm so consistent that local residents have built their lives around it. For 58 years, this pattern never changed. Scientists classified Semeru as a persistent erupting volcano, dangerous but predictable, deadly but manageable. Emergency protocols were built around its reliable patterns. Evacuation zones were drawn based on its consistent behaviour. Entire communities learned to live with a volcano that followed rules. But persistent erupting volcanoes follow those rules for a reason. They are constantly venting the enormous tectonic pressure that builds where oceanic crust plunges into Earth's mantle. Java sits directly above one of the planet's most violent subduction zones, where the Indo-Australian plate dives beneath the Eurasian plate at 7 centimeters per year. That collision creates enough molten rock to feed dozens of active volcanoes. When one of those volcanoes suddenly stops venting that pressure, it does not disappear. It accumulates. And after 58 years of accumulation, Semeru has become a geological time bomb. That could trigger the first volcanic winter of the modern era. For nearly 6 decades, Semeru has been Java's most predictable volcano. Small explosive eruptions occurred every 15 to 20 minutes. Ash plumes reached 400 to 900 meters above the summit. Pyroclastic flows stayed confined to the southeastern drainage channels. A rhythm so reliable that local tour guides used Semeru's eruptions to time their hiking schedules. This afternoon's sudden silence shattered 58 years of predictable behaviour. Dr. Cristianto Indra, head of the Semeru Volcano Observatory, was conducting routine pressure monitoring when his instruments detected the anomaly. At 2:47 p.m, all volcanic activity ceased simultaneously, he reported from the Emergency Command Centre in Malang. Gas emissions stopped, seismic tremors flatlined. For the first time since monitoring began in 1967, Semeru went completely quiet, but the silence coincided with pressure readings that defied all previous volcanic models. Deep magma chamber monitors showed stress levels climbing beyond 400% of normal eruption thresholds. Gas concentrations that should have been venting harmlessly through the summit were instead accumulating underground at dangerous levels. Dr. Surono, Indonesia's former chief volcanologist, explains that Semeru's silence represents an unprecedented threat. Continuously erupting volcanoes maintain equilibrium by constantly releasing pressure. When that venting stops, the pressure does not disappear. It concentrates. 58 years of volcanic force that should have been safely dispersed is now trapped beneath crystallized magma. Satellite thermal imaging reveals the scale of the underground buildup. Temperature sensors detect heat signatures 15 kilometers below Semeru's summit, climbing toward critical thresholds. Ground deformation measurements show the entire mountain beginning to inflate as trapped magma pushes against weakening internal structures. But here is what makes this discovery terrifying. Geological analysis shows Semeru's continuous eruption has been the primary pressure release mechanism for Java's entire eastern volcanic system. The mountain sits at the intersection of major fault lines that extend beneath Mount Bromo, Mount Kelud, and at least 12 other active volcanoes. According to Dr. Christopher Kilburn of University College London, who has been studying Indonesian volcanism for decades, Semeru's sudden cessation could destabilize the entire regional volcanic network. When the primary vent seals, pressure redistributes to secondary systems that may not be equipped to handle the additional stress. Real-time monitoring confirms Kilburn's fears. Seismic stations across eastern Java detect increasing activity at neighbouring volcanoes. Mount Bromo shows elevated gas emissions. Mount Kelud registers unusual ground deformation. The pressure that Semeru normally vents is now seeking alternative escape routes through volcanic systems that have remained dormant for years. The mathematics of trapped volcanic force are simple. 58 years of continuous eruption energy compressed into a single explosive potential, with the capacity to trigger coordinated eruptions across Java's most populated volcanic region. Semeru's 58-year pressure buildup represents more than a regional volcanic threat. It represents the potential trigger for the first climate catastrophe of the modern era. atmospheric modelling conducted by the Indonesian Agency for Meteorology shows that if Semeru's accumulated force releases explosively, it could inject 40 to 50 cubic kilometres of material into the stratosphere, more than any volcanic event since the Tambora eruption of 1815. At that scale, volcanic debris would circulate globally within weeks, blocking solar radiation and triggering immediate climate disruption. The agricultural implications are staggering. Java produces 60% of Indonesia's rice, feeding 270 million people across Southeast Asia. But volcanic winter affects far beyond impact zones. Computer models show that sustained ash clouds over Indonesia would disrupt monsoon patterns across Asia, affecting agricultural zones that feed 3 billion people. Historical precedent reveals the cascading nature of volcanic climate disasters. Tambora's 1815 eruption caused global temperature drops that lasted 3 years. European harvests failed completely in 1816. The year without a summer saw snow falling in June across New England. Lake and river ice was observed in July as far south as Pennsylvania. Temperature swings of over 30 degrees in a single day became common. But Semeru's threat extends beyond agriculture. The volcano sits at the centre of critical global supply chains that modern civilization depends on. The Strait of Malacca and Sunda Strait, both within range of major volcanic ash dispersal, handle 25% of global maritime trade. A sustained eruption could disrupt shipping routes that connect Asia, Europe, and Australia. The economic cascade would ripple through every continent. Indonesia supplies 23% of global nickel production, critical for electric vehicle batteries. Palm oil from Java-adjacent regions feeds global food processing industries. The country's position as the world's largest archipelago makes it a critical hub for international communications cables and shipping networks. And then there's the refugee crisis. Unlike previous volcanic disasters affecting thousands or even hundreds of thousands, Semeru's explosive potential threatens 145 million people across Java, more than the entire population of Russia. Evacuation infrastructure designed for local disasters would collapse under the logistical demands of relocating an entire island's population. The climate modelling reveals the most terrifying possibility. If Semeru's 58-year accumulation triggers coordinated eruptions across the volcanic network, the combined atmospheric injection could equal or exceed the 1815 Tambora event that plunged the world into volcanic winter. International climate scientists now track Semeru's pressure build-up as a potential extinction-level threat to modern agricultural systems. The same reliable volcanic activity that made Semeru predictable for 58 years has now made it the most dangerous climate weapon on Earth. Picture this. Semeru's 58-year pressure buildup reaches critical mass within 72 hours. The first sign comes at dawn, a massive ground deformation event as trapped magma finally overwhelms the crystallized dome. The mountain inflates by 3 meters in 6 minutes, triggering landslides that bury evacuation routes leading away from the danger zone. Then at 2:47 p.m. exactly, 72 hours after the ominous silence began, Semeru explodes with the accumulated force of 58 years of trapped volcanic energy. The eruption column reaches 45 kilometers into the stratosphere, higher than commercial aircraft fly, injecting 50 cubic kilometers of ash and sulfur dioxide into the upper atmosphere. Within hours, day becomes night across eastern Java as volcanic debris blocks the sun. Emergency services. Communications towers collapse as falling ash topples them. Hospitals overflow with burn victims and people suffocating from volcanic gas inhalation. Airport runways become impassable as ash accumulates faster than crews can clear it. But the local devastation is just the beginning. Satellite tracking shows Semeru's massive eruption column spreading across Southeast Asia within 24 hours. Bangkok plunges into twilight as ash clouds block sunlight. Singapore's shipping ports shut down as volcanic debris makes navigation impossible. Kuala Lumpur records the first measurable temperature drop as stratospheric ash begins its global circulation. Within a week, the ash cloud completes its first circumnavigation of Earth. European weather stations record unusual atmospheric readings. North American agriculture monitoring systems detect decreased solar radiation. Global temperature measurements show the first signs of volcanic winter as Semeru's debris begins its multi-year residence in the stratosphere. By the second month, the full horror of volcanic winter becomes apparent. Rice harvests across Asia fail, as reduced sunlight prevents crop maturation. European grain yields drop by 40% due to shortened growing seasons. North American corn production collapses as unexpected frost hits agricultural regions. The famine begins in year 1 and spreads across continents by year 2. What started as Semeru's 58-year pressure release becomes the climate catastrophe that triggers mass starvation, government collapses, and the largest refugee crisis in human history as billions flee agricultural failure zones. All because a volcano that erupted predictably for 58 years finally decided to erupt unpredictably for 58 minutes. To understand why Semeru's sudden silence represents a planetary threat, you need to understand the extraordinary geological architecture that's been building pressure for 58 consecutive years. Semeru sits above one of Earth's most active subduction zones, where the Indo-Australian tectonic plate dives beneath the Eurasian plate at nearly 7 centimeters annually. This collision melts oceanic crust into magma that rises through a complex network of conduits and chambers extending 30 kilometers below Java's surface. For most volcanoes, this magma reaches the surface sporadically, with explosive eruptions followed by dormant periods lasting years or decades. But Semeru has maintained what volcanologists call open conduit behavior since 1967, allowing magma to flow continuously from deep sources to surface vents. Dr. Indra Gunawan's research team. The Indonesian Institute of Sciences has used seismic tomography to map the extraordinary plumbing system beneath Semeru. Their findings, published just months before this crisis began, reveal a magma chamber complex stretching 15 kilometers horizontally and 8 kilometers vertically, one of the largest active volcanic reservoirs ever documented. The continuous eruption mechanism works like a geological pressure cooker with its valve permanently open. As tectonic collision generates new magma, it rises through established pathways and vents safely through regular explosive cycles. This process has been so reliable that scientists used Semeru as a model for persistent volcanic activity, dangerous but predictable, manageable through consistent monitoring. But the sudden formation of a crystallized magma plug transforms this safety mechanism into an explosive trap. When rising magma cools and solidifies in the upper conduits, it creates an impermeable barrier that prevents pressure release. Instead of venting safely through small eruptions every few hours, 58 years of accumulated force builds beneath the hardened cap. Current gas spectrometer readings reveal the scale of trapped volcanic potential. Sulfur dioxide concentrations underground have reached levels typically seen only during major explosive eruptions. Carbon dioxide measurements indicate magma degassing rates that should be producing massive ash plumes. But with no escape route, these gases pressurize the sealed chamber system. The most disturbing data comes from ground deformation measurements. GPS stations around Semeru show the mountain inflating at rates of 2 to 3 centimeters per day, expansion that indicates magma intrusion at unprecedented scales. If this inflation continues, structural failure becomes inevitable. Computer modelling by the Global Volcanism Programme shows that when Semeru's pressure seal finally breaks, the explosive release could exceed any volcanic event in the past 200 years. The 58 years of accumulation of volcanic force, compressed and superheated by tectonic pressure, represents enough energy to inject material into the stratosphere at levels comparable to the 1815 Tambora eruption that triggered global climate catastrophe. The unprecedented nature of the threat has forced scientists to develop entirely new eruption forecasting models based on pressure accumulation rather than traditional volcanic warning signs. For 58 years, the people of Eastern Java have lived their lives to the rhythm of Mount Semeru. In Lumajang, the closest major city to Semeru's base, residents use the volcano's regular ash emissions to plan their daily activities. Market vendors know to cover their goods when afternoon eruptions send ash drifting westward. School children learn evacuation routes that account for Semeru's predictable pyroclastic flows down southeastern slopes. But this afternoon's sudden silence has turned predictability into terror. Emergency services received over 3,000 calls from residents reporting that something was wrong with the mountain. Local tour guides cancelled hiking expeditions not because of increased volcanic activity, but because of its complete absence. The human geography of Semeru's threat zone represents one of the most densely populated volcanic regions on Earth. Within 30 kilometers of the summit, 4.2 million people live in cities and villages that have developed around the volcano's predictable behavior. Malang, with 2.5 million residents, sits directly in the path of potential pyroclastic flows. The port city of Surabaya houses 9 million people within range of major ash dispersal, but the trapped population extends far beyond Java's borders. Semeru's potential for volcanic winter affects agricultural systems that feed 3 billion people across Asia. The monsoon patterns that determine rice harvests from Thailand to Bangladesh could be disrupted by sustained ash clouds blocking solar radiation. Local communities around Semeru have no preparation for the scale of threat now building beneath their feet. Emergency evacuation plans assume normal volcanic behavior, pyroclastic flows confined to drainage channels, ash dispersal following predictable wind patterns, advance warning through escalating seismic activity. None of these assumptions apply to a 58-year pressure release that could trigger an explosive eruption with minimal warning. The economic dependency on Semeru's predictable activity makes evacuation particularly challenging. Farming communities time planting and harvesting around the volcano's seasonal patterns. Tourism operators guide thousands of visitors annually up slopes that could become death zones within hours. The sulfur mining operations that employ hundreds of local workers continue operating just kilometers from a potential catastrophic eruption site. For families like those living in Lumajang tonight, Semeru's ominous silence represents the end of predictability and the beginning of the unknown, waiting for a mountain that has erupted reliably for 58 years to finally erupt unpredictably. Right now, as you watch this video, Mount Semeru continues its unprecedented silence while pressure monitors record the most dangerous readings in Indonesian volcanic history. Indonesia's National Disaster Management Authority has declared a Level 4 emergency, maximum crisis status requiring international coordination. Evacuation protocols originally designed for predictable volcanic threats are being rewritten in real time for a scenario no one has ever faced. A 58-year pressure buildup approaching explosive release. Current monitoring shows the mountain's internal structure approaching critical failure thresholds. Ground deformation measurements indicate continued inflation at 3 centimeters daily. Gas sensors detect underground concentrations that should be triggering massive eruptions. Deep magma chamber pressure readings exceed 400% of normal eruption levels. But here is the terrifying uncertainty. Scientists have no precedent for predicting when 58 years of trapped volcanic force will finally explode. Traditional eruption forecasting relies on escalating warning signs, increased seismicity, accelerating gas emissions, rapid ground deformation. Semeru's crystallized plug could maintain pressure for months or catastrophically fail within hours. Dr. Cristianto Indra, coordinating the emergency monitoring effort, admits the unprecedented nature of the crisis. We are tracking pressure levels that exceed our scientific models. Semeru's 58-year accumulation represents uncharted territory in volcanic science. As international rescue assets position around Java's coastlines, as atmospheric scientists track potential climate impacts. As agricultural monitors prepare for possible global disruption, one question dominates every expert analysis. When Semeru breaks its terrifying silence, will the sound be heard around the world? Semeru's 58-year countdown may have just stopped, with 145 million people trapped in the blast radius of the largest volcanic time bomb in modern history. When volcanic winter begins, only those with advanced knowledge will be prepared. Subscribe to Earth Attacks Now for critical early warnings and survival strategies that mainstream media will not report until it is too late.